In this lesson, we're going to continue with volumes of rotation, but this time we're going to be looking at a function, well, two functions put together. So we have an outside curve and an inside curve. And so rather than getting disks, we're going to be getting washers. The basic idea is still the same. We're looking at the area of each cross-section in order to find the volume. And so we'll still follow the same basic steps, but the setup is going to look a little bit different. The basic idea, again, is that we have a top curve, or an outside curve, and a lower curve, which is on the inside. Rotating this one around the x-axis is going to cause this to spin. Notice that we have an inside radius and an outside radius that are different. And so the shape that we're getting at any point will have a hollow inside, and so we're getting these washer shapes where the inside is cut off. In this one, I'm rotating two curves I got on top, the square root of x, and on the bottom, x squared. And we're looking at the region that they enclose, so we're going from 0 to 1. If we take our radii, we would be drawing them from the inside. So your lower radius would be going perpendicular to the x-axis up to your lower curve. The larger radius is going up all the way to the top curve. Now, if we consider the rings that are formed, then these are now rotated around the x-axis. Notice it would look something like that, on the bottom like that. So we get a full ring coming up both off the page and below the page. If I move to another spot on my graph, you should notice that the ring's going to look a little bit different. Notice that the inside is very small, the outside is wider. Overall, the ring is smaller, but it's much wider. This is a much more narrow ring, and so the area is going to be very different at each point here. If we look at this cross-section of it, as we move from left to right on this, notice the basic shape of this, if we're just looking at what it's doing on the two-dimensional plane, is going to be a reflection of that original graph. And so when we draw these, what we want to do is reflect that curve as our first step. And so the lower function would come down about to here, the upper function would come about to here, and then we're going to get all these rings as our cross-sections drawn on there. Now these can also be drawn and rotated in the other direction. This one's being rotated around the x-axis, and so my radii are drawn perpendicular to the y-axis. If we look at the reflection then that's caused, notice we're going to get the same shape on both sides. So if you know what it looks like between the curves, you just reflect that over the axis as your first step. If we consider the rings that are formed, you're going to look something like that. And again, they'll look different. They'll have different sizes wherever you are on the curve, but they will always have a smaller radius for the inside ring and a bigger radius for the outside ring. The area of our cross-sections then are going to be the areas of two circles and then subtracted. So the larger radius and the smaller radius, and you have the area of each of those. Notice also that when you put these into the formula for volume, a lot of times they'll just factor the pi out, leaving us with an integral with the big radius squared minus the smaller radius squared with respect to whatever variable we're using there, and remembering the limits of integration. So to solve a problem like this, we have a few steps. The first step then is to sketch the solid, which we get by just graphing the two curves. In this case, we're dealing with sine of x and cosine of x, which if we look closer, the cosine of x is on top and the sine of x is on the bottom. Now I would recommend reflecting these over the axis, so as we bring it down, the inside curve and then the outside curve will come like that. We want a typical cross-section, so we're going to think about the radius that we're forming, first of all, the inside one is going to look like that. And so for that cross section, we'll use a small r. And then the bigger one coming up beside that is going to create a larger ring. And so its radius will be the big R. Notice that the big R then is going to be cosine of x, and our smaller r is sine of x. So as we look at the way that these washers are growing, each washer is running sort of slicing the x-axis, which means these are small changes in x, which means we need to do everything in terms of x. For this one then again, the smaller r was the inside function, that's sine of x. The larger r was the outside function, which was cosine of x. And so if we want the area of this thing, it'll be the area of the big circle, which was pi r squared, and the big circle was cosine of x. Then we subtract the area of our smaller circle, which was sine of x. And that's radius, so it's squared. Our next step then would be to find the limits of integration. Now we've already noticed this is going to be in terms of x, and so I look what that's doing. It's starting here at 0, and then it's stopping over here at some point that was not given to us. And notice that's the intersection of the two curves, so what I'm going to want to find is when sine of x is equal to cosine of x. Using my calculator, I found that value to be about 0.7864. And so that's the limit I'm going to use here. We're going to write out our volume then with an integral. Now often the pi will be factored out. We're starting at 0 to 0.7854, and then we subtract our larger radius squared minus our smaller radius squared. And that was with respect to x. Again, remember to choose your x and y based on which direction we're stacking the disk, or thinking about what our radii are perpendicular to.